The sun just did something that sent shockwaves through the cosmos. A massive, dark hole tore open across its surface, releasing a river of charged particles that surged toward Earth. At that exact moment, something else happened, something no one could explain. Comet Atlas, a mysterious interstellar visitor, vanished from every telescope in the world. Moments later, the ground itself began to shake. Across the planet, scientists and sky watchers alike asked the same question. What just happened? Was the comet destroyed, transformed, or hidden from view? And if it returns, will it even be the same? As Atlas disappeared, another celestial wanderer entered the scene. Comet Lemon, a frozen relic older than humanity, was racing across the heavens, and experts warned the next 2 weeks could reveal something extraordinary. Meanwhile, in China, physicists announced what sounded like science fiction, a secure communication network said to be completely unhackable. And before this story ends, a few cosmic dates loom ahead that no one is talking about but should. October 2025 began with a silent warning from the sun. High above, instruments detected an enormous coronal hole stretching across the solar equator, an opening so vast it looked like a wound bleeding invisible energy into space. This wasn't the gentle activity that paints the night sky with auroras. This was a rupture spanning both hemispheres of the sun, a configuration rarely seen and poorly understood. Through that opening streamed the solar wind, blasting outward at nearly 700 kilometers per second, about 1.5 million miles an hour. Each particle, a tiny bullet of plasma, was hurled directly toward Earth. Even stranger, the magnetic polarity of the wind lined up perfectly with our planet's magnetic field, creating the ideal conditions for energy to transfer straight into Earth's magnetosphere. To scientists, the alignment looked almost too perfect. Emergency bulletins went out. Power grid operators braced for overloads, satellite controllers prepared for malfunctions, and aurora chasers raced north with their cameras. The sky, they knew, was about to burn with color. But something else unfolded at that same moment. Comet 3, I Atlas, only the second confirmed interstellar visitor ever seen, slipped behind the sun and vanished. One heartbeat, it was there. A pale smudge of alien light. A traveler from another star system, carrying dust older than our sun. The next, it was gone, swallowed by the sun's blinding glare, erased from every telescope in orbit and on Earth. The coincidence was impossible to ignore. Earth was being bombarded by the fastest solar wind in months, and our only interstellar messenger disappeared behind the very source of that storm. Scientists cautioned restraint. Correlation, they reminded everyone, is not causation. But then the earthquakes began. Within hours, several magnitude 7 tremors struck across the globe. Seismographs recorded the violent jolts, massive energy released from deep inside the crust. Technically, such quakes weren't rare. The Earth averages about 15 a year. But having several so close together, right after a major solar eruption, stirred humanity's oldest instinct, the need to find meaning in coincidence. Could the sun's magnetic outburst have somehow triggered the quakes? Most geophysicists said no, tectonic plates don't respond to magnetic fields. They move according to stress and rock mechanics, not solar wind. Yet, at the fringes of the scientific world, a few voices whispered about patterns, about statistical oddities linking solar cycles with seismic waves, about minute shifts in Earth's rotation that might play a role. Nothing proven, yet not entirely dismissed either. Still, the true mystery lay in the missing comet. Comet 3, I Atlas, was more than a streak of ice and dust. It was a messenger from another star. Only 2 others had ever been seen before it. Oumuamua, discovered in 2017, and 2I Borisov, found 2 years later. Oumuamua baffled scientists, an elongated object tumbling through the solar system, accelerating in ways gravity couldn't explain. Borisov, by contrast, looked familiar. A glowing ball of ice and gas behaving like a classic comet, proof that the chemistry of distant worlds might mirror our own. Then came Atlas in 2025, racing toward the sun on a path too fast for capture, a visitor just passing through. For researchers, it was priceless, a rare chance to study material forged around another star, long before our planet even existed. Every photon of light it reflected carried secrets about alien chemistry, about how other solar systems form. And then, without warning, that light went dark. When Atlas slipped behind the sun, we lost more than a comet. We lost our window into another world. Now astronomers ask a haunting question. When it reemerges, if it ever does, will we even recognize it? Did the sun's fire destroy it, or transform it into something new entirely? Whatever comes next could rewrite everything we know about these ancient wanderers that drift between the stars. Its story began months earlier, with a faint streak of motion captured by Hawaii's Atlas survey, the Asteroid Terrestrial Impact Last Alert System. Designed to detect dangerous asteroids, the system scans the skies every night for anything that moves. But one image showed something extraordinary. Follow-up observations confirmed it. The object wasn't bound to the sun. Its orbit was hyperbolic proof. It came from beyond our solar system. Astronomers around the globe dropped everything. Telescope schedules were rewritten, spectrographs aimed skyward, and every observatory raced to gather data before it vanished again. They studied its brightness, hoping to learn its composition. But Atlas didn't behave like any normal comet. Instead of brightening steadily as it neared the sun, its light curve pulsed periods of calm, followed by sudden bursts of brilliance. The coma surrounding it was faint, almost ghost-like. Some said it was dense and rocky. Others argued it was fragile and porous, like a pile of dust barely held together by gravity. And the orbit, unstable. Jets of gas erupting from its surface acted like tiny thrusters, constantly nudging it off course. Each recalculation changed the predictions, widening the uncertainty until no one could say exactly when or where it would appear again. Then came the last images, blurred, stretched, uneven, suggesting the comet was already fragmenting. If it was breaking apart before disappearing, what would be left after facing the sun's fury? Astronomers called it the invisible interstellar traveler. Somewhere beyond the glare, a fragment of another world was either holding together or coming undone. All humanity could do was wait. The sun is not kind to visitors. We think of it as life-giving, but up close it's a raging sea of plasma where magnetic storms twist like serpents. When those magnetic coils snap, they unleash energy powerful enough to melt stone, disrupt satellites, and strip atmospheres from planets. The coronal hole of October 2025 was one of the most violent in recent memory. Most solar wind travels at around 400 kilometers per s. But this storm screamed outward at nearly 700 kilometers per s. When such a gale collides with a comet, the encounter becomes a cosmic battle. Unlike Earth, a comet has no magnetic shield. The solar wind hits it head-on, striking the coma, a cloud of vapor and dust surrounding the nucleus. The gas becomes electrically charged, and the sun's magnetic field wraps around it like a glowing shroud, forming the iron tail that stretches for millions of kilometers. That tail flickers, ripples, and sometimes tears away entirely before reforming. Each event a clue to the unseen forces raging through space. But what happens when a comet already weakened by heat faces such a storm? history gives us grim lessons. Comet Ison, once hailed as the comet of the century, disintegrated in 2013, reduced to a fading trail of dust. Yet Comet Lovejoy, which skimmed just 140,000 kilometers above the Sun's surface in 2011, miraculously survived. No one can fully explain why it simply refused to die. Now 3I Atlas was making a similar dive, not as close, but into a far more hostile environment. Could heat, radiation, pressure, and fragmentation together spell its end? Some scientists believed yes. Others whispered more exotic theories. A fringe group of plasma physicists proposed the electric comet model, suggesting that comets interact electrically with the solar wind, building up charges that could trigger sudden explosions or unpredictable shifts. Mainstream astronomy rejects this idea. Classical physics, they argue, explains everything we see. Yet, as Atlas vanished during one of the strongest solar storms in years, even skeptics found the timing unsettling. The truth is, we don't yet know what Atlas is made of. Spectroscopic readings were incomplete. Perhaps it's rich in water ice, perhaps in carbon monoxide or silicate rock. Each possibility means a different fate. A porous nucleus could crumble like ash. A rocky one might endure. The Sun, acting as both destroyer and gatekeeper, would decide which. If Atlas emerges whole, it proves that interstellar comets are stronger than we think. If it's gone vaporized or scattered into dust, then we've just witnessed how fragile these cosmic wanderers truly are. Either way, the universe just reminded us how small we are in the face of its fire. Astronomers believe that if Comet 3I Atlas survived its close encounter with the Sun, it should soon reappear. Most predictions point to late October or early November 2025, when it will move far enough away from the Sun's glare to be visible again through specialized equipment. The first to search for it won't be backyard observers, but space-based telescopes, machines built to block sunlight and peer directly into the blinding zone where comets hide. The Solar and Heliospheric Observatory SOHO will likely lead that search. Its coronagraphs create artificial eclipses, allowing scientists to see what lies just beside the Sun, precisely the region where 3I Atlas vanished. The Solar Terrestrial Relations Observatory, better known as STEREO, will join the effort, using its twin spacecraft positioned around the Sun to provide multiple viewing angles. If luck is on their side, one of them might spot the comet before Earth-based telescopes even get the chance. Far closer to the fire, NASA's Parker Solar Probe continues its daring mission, flying deep inside Mercury's orbit through regions where solar winds scream at unimaginable speeds. If the probe's path happened to cross near the comet during conjunction, its instruments might have recorded priceless data, the kind no telescope on Earth could ever capture. But Parker wasn't built to hunt comets. Its focus is the Sun itself, the corona, the plasma, the solar wind. Unless the comet drifted directly into its field of view, the instruments would have missed it entirely. And so far, mission scientists have announced no lucky encounters. The geometry simply didn't line up, or perhaps the comet was already too faint to see. So the world waits for the first recovery images. Best case scenario: the comet reappears, perhaps dimmer from dust loss, but still alive, with a faint halo and a tail shimmering behind it. Its spectrum would show familiar fingerprints: water vapor, cyanogen, carbon monoxide, the basic chemistry of an active comet. Astronomers would compare its brightness to the data gathered before conjunction, measuring how much mass it lost while hidden in the Sun's fury. Worst-case scenario: nothing appears. The sky remains empty where 3I Atlas should be. No glow, no trace, only the silence of deep space. That would mean the nucleus shattered into fragments too small to detect or vaporized completely, leaving nothing but an invisible haze. It wouldn't be the first time. Many comets have perished after flying too close to the sun. Their loss becomes another entry in the quiet ledger of cosmic destruction, a lesson in how fragile these travelers truly are. Yet between those two extremes lies a spectrum of possibilities. Perhaps 3I Atlas returns, not as a single body, but as a chain of fragments, a string of pearls scattered along its orbit. Each fragment would be faint, but together they'd tell a story of how and when the nucleus broke apart. Astronomers could study their spacing and speed to reconstruct the comet's final moments before it fell apart. Another possibility is dormancy. If the comet exhausted its surface ices, it might have developed a hardened crust that blocks further outgassing. Without fresh ice exposed to sunlight, it would no longer shine. It would look like a small, dark asteroid, cold, quiet, and deceptively ordinary. In that case, we'd lose our ability to study its chemical makeup. But we'd gain clues about how cometary crusts form and how these bodies age in the heat of the sun. And then there's the most fascinating outcome of all: unexpected brightening. Sometimes, a comet breaks open just enough to expose untouched layers of volatile, rich material beneath the surface. When that fresh ice meets sunlight, gas erupts violently, making the comet blaze far brighter than before. If Atlas fragmented this way, it could reappear in pieces, but more luminous than ever, a final burst of beauty before fading forever. The show, however, would be short-lived. Once those smaller fragments burn through their reserves, they dim quickly, fading back into obscurity. Spectral data will hold the answers. Before the conjunction, scientists detected only partial chemical signatures, mainly water and carbon monoxide. Now they hope to see what else lies within. Oxygen emissions would confirm sublimating ice. Cyanogen would point to carbon-nitrogen compounds. Sodium and iron lines could suggest that deeper, metallic layers have been exposed. Each spectral fingerprint tells a story, a postmortem of a cosmic visitor's final trial by fire. But it isn't only professionals who will be watching. Amateur astronomers, equipped with backyard telescopes and powerful digital cameras, form a global web of observers. Unlike large observatories bound by strict schedules, they can scan the skies continuously, night after night. If 3I Atlas reappears suddenly or splits into smaller fragments spread across the heavens, it might be a hobbyist, not a NASA scientist, who spots it first. Modern software allows these independent observers to produce results rivaling those from major institutions. In this new age of crowdsourced astronomy, anyone under a clear sky can help write the next chapter of this unfolding mystery. At any moment, the comet could reveal itself or not at all. Days could pass, then weeks, with nothing but silence, until astronomers are forced to admit that 3I Atlas is gone, destroyed by the very star it came to visit. The uncertainty is both maddening and exhilarating. No probe was sent to meet it. No instruments were close enough to see its fate. All we can do now is aim our telescopes, wait, and wonder. But a deeper question troubles the minds of those who study it. If the nucleus is gone, if every trace of the comet has scattered into dust, do we still have 3I Atlas? Or has it ceased to exist? It's a philosophical puzzle worthy of the ancients, echoing the ship of Theseus' paradox. If every piece of a wooden ship is replaced, is it still the same ship? And if a comet splits into 1,000 fragments, each following the same orbit and carrying its original material, are they together still the comet, or merely its remains? There's no official definition. Some would say the identity persists through its orbit and composition. Others would insist it died the moment it lost its core. But for many who spent months tracking it, the question feels personal. 3I Atlas was more than data. It was a physical connection to another star system, a messenger from the deep galaxy. Losing it feels like losing a bridge to somewhere unimaginably far away, a thread that linked us to the wider universe, severed just as we were beginning to understand it. Why does all this matter to anyone beyond a few astronomers and science journals? Because humans are creatures of pattern and meaning. When we see events like these, the sun erupting, an alien comet vanishing, and powerful earthquakes shaking the Earth in the same window of time, our collective instinct screams. Something is happening. Whether it's coincidence or connection, it stirs that ancient sense of awe and unease that reminds us how small and how curious we truly are. The mainstream view in geophysics is simple and firm. Earthquakes come from plate tectonics, not from the sun. Tremors happen when slow, steady motion of Earth's plates builds stress in the crust until locked faults finally slip. By that logic, solar activity shouldn't matter. Magnetic fields don't move rock. The solar wind is stopped high above us by the magnetosphere and the air. The sun's heat at Earth's surface is tiny compared with the planet's own internal heat. Decades of studies comparing quake catalogs with solar cycles have found nothing beyond chance. And yet, patterns keep teasing the eye. Hints appear, fade, and return, never strong enough to pass strict statistics, never weak enough to silence curiosity. So a few researchers keep asking careful what-ifs. Could solar storms disturb the ionosphere and subtly change the electrical properties of faults already near failure? Could tiny shifts in Earth's spin or magnetic orientation, driven by momentum in the solar wind, nudge a stressed fault past its tipping point? Might there be some electromagnetic coupling between the upper atmosphere and conductive layers in the crust that we don't fully understand? These ideas face heavy skepticism. Extraordinary claims need extraordinary proof, and so far the evidence is circumstantial. But people don't think in p-values. We think in stories. When the sun erupts, big quakes hit, and an interstellar comet vanishes, all in the same news cycle, the story writes itself, even if the physics says otherwise. The interstellar part adds fuel. Objects like 3I Atlas come from beyond our solar system, formed in places we can only imagine. They are, in the strict sense, alien, and humanity has always projected hope and fear onto the unknown. When Oumuamua sped away with a small, unexplained push, many jumped to ideas of probes and light sails. Natural explanations remain most likely, but the mind loves a mystery more than a paper on carbon monoxide outgassing. So when Atlas disappears during a solar storm, speculation blooms. Did it carry something? Are we watching a cosmic quarantine? The sun burning down threats before they reach the inner planets. Scientifically, those notions don't hold up, but their psychological pull is strong. We want the sky to mean something. We want comets to be messengers, not dirty snowballs. Even panspermia, the idea that comets seeded early Earth with life's ingredients, gives that longing a scientific sheen. If an interstellar comet is a true sample from another system, losing it would feel like a library burned before we read it. More exotic claims persist. Electric universe voices point to odd brightness swings, disconnection events, and the fierce solar wind, saying only electrical models can explain them. But the math rarely matches observations, and predictions often fail. Still, lightning and sparks make for gripping imagery, and gripping ideas can outlast weak evidence. Then come the conspiracies. Are space agencies hiding Parker's solar probe data? Did instruments catch Atlas doing something impossible, changing course, emitting signals, and someone buried the truth? These scenarios are vanishingly unlikely. Yet for minds primed to distrust, no news becomes proof of a cover-up. Conspiracies offer comfort. A hidden plan is easier to accept than a chaotic universe, where quakes strike at random and comets crumble for no reason. But reality is tricky. Sometimes coincidences really do pile up. The October 2025 trio solar storm, comet disappearance, and strong earthquakes might be just that. A rare cluster that grabs our attention and, in the end, means nothing. Or it could be a faint clue of links we can't yet measure, weak, indirect ties between space, weather, and geophysics. Science moves by testing anomalies, not by ignoring them. Most likely, careful searches will find no causal bridge. Still, the search itself matters. When Atlas returns, if it returns, it may be changed. The comet that went in might not be the comet that comes out. And when papers appear with sober explanations grounded in physics and chemistry, many will nod and move on. Others will keep looking for a deeper pattern that stitches sun, quakes, and comet into a single design. Both reactions are human. Both try to make sense of our small place in a vast, mostly silent universe. Meanwhile, there is a comet you can see. While Atlas plays hide and seek behind the sun, Comet Citwadi 25A6 Lemon is putting on a show for anyone willing to look. Discovered by Mount Lemmon Observatory, it's now brightening toward mid-November 2025 perihelion. The next 2 weeks are prime time. It should sit far enough from the sun's glare to catch with binoculars or a small telescope, and under truly dark skies, possibly even the naked eye. Wake before dawn or watch after dusk. Get away from city lights, and you might witness a different kind of message from the deep one that doesn't argue or warn, but simply shines. Right now, Comet Lemon is visible in the pre-dawn eastern sky, rising a few hours before sunrise. Through binoculars, it glows with that soft, hazy light unique to active comets around Coma, maybe even a short tail. Its brightness sits between magnitude 4 and 5, right at the edge of what the unaided eye can see. Under dark skies, away from city lights, magnitude 4 should be visible, but knowing exactly where to look helps. At the moment, the comet drifts through the constellation Cancer, sliding slowly eastward. Finder charts online trace its path across the stars, showing exactly where to aim a telescope. Comet observing demands patience and darkness. Unlike planets, which shine as compact points, a comet spreads its light across an area, so it fades quickly in light-polluted skies. In a bright suburb, you might still see fourth magnitude stars, but a fourth magnitude comet will vanish completely. To find it, you need to escape the glow somewhere the Milky Way arches overhead, and the sky itself feels deep. Binoculars are perfect for the task. A pair of 750s, common among birders and skywatchers, offers just enough magnification to gather light, yet keeps a wide view that makes locating the comet easy. Mounting them on a tripod steadies the image and lets you study longer without fatigue. In the lenses, Lemon will appear as a faint, fuzzy patch, slightly green from glowing carbon molecules in its coma. A small telescope can show more detailed jets, fans, or the first hint of a tail, but the narrow field makes tracking harder. Many veterans still prefer binoculars. The wide view shows the comet floating among the stars, a traveler moving through permanent company. Early measurements of Lemon made scientists both nervous and excited. Its brightness refused to follow the models. Comets are notoriously unpredictable because their glow depends on things we can't see directly: the nucleus size, rotation, texture, and the balance between dust and gas. Lemon brightened faster than expected. then held steady in puzzling plateaus even as it neared the sun. Several explanations could fit. It might have had outbursts, where new volatile ice suddenly vents, flooding space with gas and dust. Or its rotation could be bringing alternating hemispheres into sunlight, each with different levels of activity. The darker possibility is fragmentation, the nucleus beginning to crack apart under heat and stress. That's the hidden risk for every comet. It can look perfectly healthy until one day it simply breaks. Sometimes a large piece separates and drifts beside the main body. Sometimes it crumbles entirely into countless fragments, too small to see, their combined surfaces flaring briefly brighter before fading away. The physics behind that collapse is brutal. Comet nuclei are fragile, more like compressed snow than stone, held together by their own weak gravity and thin icy bonds. As one side heats up, expansion creates internal stress. Spin adds more tension, and jets act like thrusters, twisting the nucleus faster until cracks spread and the body splits apart. In Lemon's case, the driver may not even be water. Data hint that carbon monoxide and carbon dioxide ices are fueling its activity. These ices vaporize at much lower temperatures than water, letting the comet stay active even far from the sun. As it closes in and warms, water sublimation will take over, often changing the pattern of brightness altogether. The tails tell the rest of the story. The ion tail, made of charged gas, will stream straight away from the sun, swept by the solar wind like a cosmic windsock. The dust tail will curve gently, its particles pushed by sunlight, but still carrying the motion of the comet itself. In long exposure photographs, the two tails often separate into distinct, graceful arcs. One electric blue, one golden. For now, the show belongs to the patient. Under quiet skies before dawn, Comet Lemon hangs low on the horizon, another fleeting messenger, whispering through the darkness, while its interstellar cousin remains hidden behind the sun. Comet Lemon's ion tail glows faint blue, lit by carbon monoxide ions streaming away from the sun. It's straight and tense, often marked with small streamers or knots that reveal the turbulence of the solar wind. The dust tail, broader and softer, shines yellow-white in reflected sunlight, curving gently away from the nucleus like a long, glowing veil. Comparing Lemon to 3I Atlas reveals just how different native and interstellar comets truly are. Lemon was born about 4.6 billion years ago, inside the swirling disk of gas and dust that surrounded the infant sun. It likely formed beyond Neptune, where temperatures were low enough for water, carbon dioxide, and other gases to freeze into ice. Gravitational nudges from the giant planets eventually flung it into the Oort cloud, that vast, invisible sphere of comets encasing the solar system, stretching more than 100,000 astronomical units from the sun. For billions of years, it drifted there in darkness, until something, perhaps the passing gravity of a distant star, disturbed its orbit and sent it falling homeward once again. Lemon's chemical fingerprint tells the story of our own solar nursery. Isotope ratios and molecular patterns formed from the same material that built Earth. 3I Atlas, on the other hand, was born somewhere else entirely, around another star, in a different cloud, under alien conditions. The temperature, pressure, and radiation levels of that long-lost system, even the timing of its planets' births, shaped what its comets became. Studying interstellar visitors like Atlas beside comets like Lemon is like comparing samples from different stellar nurseries, a chance to discover what's universal and what's unique in the recipe for creating worlds. Lemon reminds us how fragile comets are. Everyone is a gamble against destruction. Most survive their close passes with the sun, losing some ice before retreating back to the cold frontier. Some fragment spectacularly, breaking into multiple glowing pieces that brighten, fade, and vanish. And a few, too fragile, or unlucky disintegrate completely, erased so thoroughly that not even their trails remain. Watching Lemon this season is more than stargazing. It's witnessing a survivor, an ancient relic that has spent eons frozen in the edge of the solar system and is now facing the heat and radiation of its creator. While Atlas hides behind the sun, Lemon becomes our stand-in, a living subject to study and admire. If you've never seen a comet with your own eyes, now is the time. Go out before dawn. Find a dark, open sky. Give your eyes 15 minutes to adjust and look toward Cancer in the east. That faint, fuzzy patch of light you find there carries ice older than Earth, dust older than the planets, and organic molecules that predate life itself. You're looking at a messenger from the beginning of time, one that will soon fade back into darkness, its fate still unwritten. Comets often travel in groups, or at least, it seems that way. At any given moment, dozens orbit the sun, most invisible to all but the largest telescopes. A few grow bright enough for amateurs to follow, and once in a generation, one becomes a household name. The clustering we notice is partly illusion, more a reflection of how many eyes and instruments are watching. But 2025 truly seems like a year of comets. Alongside Lemon and the vanished Atlas, astronomers have now confirmed another, Comet Ceatwoidine 25 R2 Swan. It's named after the Swan instrument aboard the SOHO spacecraft, which scans the heavens in ultraviolet light, detecting hydrogen released when sunlight splits water molecules apart. Comets generate vast, invisible hydrogen clouds, sometimes millions of kilometers wide, and Swan can spot them long before the visible coma ever forms. Swan's optical conformation revealed an elongated orbit that will bring it closest to the Sun in early 2026, long after Lemon fades, but soon enough to keep excitement alive. Initial estimates place its brightness between magnitude 6 and 7, just below naked eye visibility, but easily seen with binoculars. Of course, comet predictions are famously unreliable. Some Swan discoveries have surprised astronomers, flaring brilliantly as they neared the Sun. Others remained faint ghosts, forgotten almost as soon as they appeared. The only way to know is to wait and watch. There's also the potential for something more spectacular, a meteor shower. As a comet travels, it leaves a trail of dust behind, a thin ribbon of debris orbiting the Sun. If Earth later passes through that trail, the particles slam into our atmosphere at tens of kilometers per second, burning up in streaks of light. Most of our annual meteor showers, the Perseids, in August. The Geminids in December come from old, well-established dust streams. But a new comet like Swan can release fresh clusters of particles in unpredictable patterns. If our planet happens to cross one of those dense knots, the result can be breathtaking. A meteor storm with hundreds or even thousands of visible streaks per hour. Such events are rare and nearly impossible to predict precisely, but even the small possibility electrifies skywatchers. During such storms, meteors seem to radiate from one point in the sky. The radiant, their parallel paths, bending into perspective lines. When it happens, the effect is overwhelming. Streaks of light pouring from the stars, turning the night into a living sky. But not every comet fulfills its promise. History is full of false dawn's comets that should have blazed bright, but fizzled instead. Comet Kohutek in 1973 was hailed as the comet of the century, but barely reached the threshold of naked eye visibility. Comet Ison in 2013 was expected to survive its close pass and brighten spectacularly, but disintegrated before the show began. These humbling reminders teach patience. Comets obey their own physics, not our expectations. Still, every success and every failure teaches us something. comparing Swan and Lemon, their brightness curves, their activity, their survival will give astronomers a rare side-by-side look at comet behavior under nearly identical solar conditions. Differences in brightness or structure may reveal what each comet is made of, whether one is water-dominated and the other carbon monoxide-driven, whether one fragments easily while the other endures. In this cosmic dance, Lemon and Swan become foils, one visible now, one still preparing its approach, both carrying lessons about the fragile nature of these frozen worlds. And all of it unfolds under a restless sun.